Hello, welcome back. So today we're going to start section 2.3 from my proofs book. And as I'm talking, I'm noticing that my wound has yet to heal. Yeah. In case you're wondering, I'm okay. I just ran into a tree. It's don't laugh at me. It's slightly less embarrassing than it sounds because I was playing with my kids. There were these bushes that the branches really went out before the leaves started, and there weren't so many big branches, which created this nice little hideaway fort that they could hide away in. And so they were playing in there. I was trying to sneak around to surprise them. There are also these trees growing around with these horizontal branches, and I come around the corner to surprise them, and I run into a tree. So that's what happened. It's actually looking quite a bit better than 2 days ago. Happened over the weekend. Anyways, enough of that. Let's talk about divisibility. So definition 2.8 in the book says that a non-zero integer a divides an integer b if, and there's a blank. So how would you complete this sentence? If you were defining this term, because some human define this term, how would you define it? Intuitively, you might know what it means for a number to divide another number. Like you would say, 3 divides 15. So why does 3 divide 15? Well, if you take 15 divided by 3, you get 5, which is an integer. Okay? So you could say 3 divides 15 because 15 divided by 3 is an integer. So that would be a fine definition. A divides b if b divided by a is an integer. Okay, that's period. That sentence would be a perfectly fine definition. It is equivalent to the definition I'm going to give you. It's equivalent to many other definitions. But we've talked before about how definitions are human inventions. They should be chosen intentionally. They should be chosen for their usefulness. If there's many ways to define something, define it in the way that's going to be most useful to you as a mathematician. For example, we talked about what does it mean to be even? Well, if you have an even number n, by definition of even, that's equal to 2 times k for some integer k. All right? So that's useful because now every time, think about the last few videos that you watched, the last few times that we had a problem and it said assume n is even, we can just substitute 2k in for n, right? So we can sub in 2k every place we see an n. And that was very useful for actually solving our problems. So in a similar vein, we want to create a definition, which in fact is very similar to this one. That's not a coincidence. A definition which is useful to work with. So take a moment and think about how you would define it. Yeah, you could say a divides b if, you could say, you want to do b over a, that's the basic idea, but instead of saying is an integer or equals an integer, we basically want to have this this a on the other side of the equation. Does that make sense? If it's on the other side of the equation, first of all, multiplication is just sort of easier to work with than division, and we have this sort of substitution thing happening potentially. Let me show you what I mean. So this is the definition. If b equals a times k for some integer k. It's very similar to definition 2.2 of an even number, as it should be, because I mentioned that this is sort of another level of abstraction from like the definition of an even. Well, that's exactly right. What does it mean to be even? It means 2 divides you. So what does it mean to be, so this is saying, not only do we want to say, what does it mean to be even, 2 dividing you, what does it mean to be divisible by 3, to be divisible by 4? They should all have similar definitions, and indeed they do. Okay. So being even means 2 divides you. You could imagine another definition of meaning 3 divides you. Perhaps we could even call that 3 even. Okay, so being 3 even means 3 divides you. And you could just sort of imagine this for anything. So that's what it means for A to divide B. It means you have this equation. So that is a smart definition that some mathematicians chose. We also have notation saying A divides B. This is the notation that's used. There's this tall bar that's drawn. So A divides B is written like this. Okay, this means A divides B. You know, it's kind of like this, B divided by A with a horizontal line, but that's already taken, right? If it's a horizontal line, that's asking for an arithmetic operation. We actually take 15 divided by 3. This is not an arithmetic operation. This is a claim. It's a statement. It's saying A divides B. It's either true or false. It's not 5 or 7 or some other number. It's either true or false. So, you know, that's how you should be thinking about this symbol and how it differs than the horizontal bar symbol. So A vertical line B means A divides B. We also have something that means, that means A does not divide B. So what would that notation be? Well, we already have another notation that adds a does not in it. You know, we have x equals y. You know that notation. How about x does not equal y? We put this slash through it. Okay? So, too bright on the screen? I keep thinking it's too bright. So putting a slash through it means does not happen, does not equal y. In a similar way, what would the notation be? It's A vertical line with a line through it, B. So that's the notation for A does not divide B. So sensible, good notation. Now let's do some examples of division. So 2 divides 14 was my first example. You agree? 2 does divide 14, right? Because if you take 14 divided by 2, you get 7. That's an integer. So yes, it evenly divides it. Evenly reasonable use for it in this case. But that's not the actual reason why 2 divides 14, because now we have a definition. So the reason 2 divides 14 is because it satisfies the definition. Okay, so from this point on, if you have a definition, that is what is used to determine whether something does happen or does not happen. So 2 divides 14 because 14 equals 2 times 7. And at least for the first one, I'll say, and 7 is an integer. Okay. So that's why, because you can write it as 2 times an integer. 14 can be written that way. Okay, let's do another one. One for does not divide. 6 does not divide 9 because 9 equals 6 times 1.5. So this is not an integer. I'm running out of space, so I'll just sort of slip it up here. Sloppy, not an integer. Okay. And we could do others. Let me see if I can put a couple more in here. So we have 12 divides negative 48. Somebody asked, does it work for negatives? Well, yes, it does. The reason is because negative 48 equals 12 times negative 4. Okay? Negative 4 is an integer, right? This only says integer. It doesn't say positive integer. It says integer. So negative 4 is an integer. So yes, 12 does indeed divide negative 48. Here's let's see. Does A divide 0? So if A is a number, an integer, does A divide 0 or does A not divide 0? Which way is it? Well, we can check, right? Funny things happen with 0, especially when you're talking about divides. So let's go up here. So 0 would be the b. So b equals a, so 0 equals a times an integer. Is there an integer for which 0 equals a times that integer? Yes, 0, right? The k would be 0. So anything divides 0. This is true for all integers a, okay? What about 0 dividing b? Does 0 divide b? Let's see. So if b is an integer, let's just pick one, 2. Does 0 divide 2? What does 2 equal 0 times an integer k? Can you find an integer k for which 2 equals 0 times it? No, you cannot, right? So as long as b is not 0, if it is 0, then we're back in this case. But if it's non-zero, then you say does not divide. Make sense? For all non-zero integers b. Okay, I know I'm squeezing that in there. Hopefully it's clear enough. Okay. So there you go. Hopefully this definition of divides makes sense. And if it does, then that means we are ready for our first proposition. Whenever we learn something, we should combine a new concept with practicing our proofs. Speaking of my kids, my kid was in here wanting to draw all over this board, which we did, which was fun, but he also rubs his oily fingers all over it. And then it makes it harder to erase with my rag of a wiper. Okay. So here's the proposition. Let me look up what this is. This is proposition 2.10. Proposition 2.10 in the proofs book. So let A, B, and C be integers. So that's the setup. You have to have integers in order to even talk about divisibility. So let's start with integers. If A divides B and B divides C, then what's the conclusion, do you think? If 2 divides 8 and 8 divides 16, what do you think I'm going to say is the next step? 2 divides 16. Does that make sense? Do you believe it? So if you started playing around with examples of divisibility, and you said, well, what could be something that I might be able to prove regarding divisibility? Something that you might think about is combining them, having a couple of divisibilities next to each other, like A divides B and C divides D, and saying, well, how do these relate to each other? And then you might start noticing, well, if C and D, or B and C, in my language from a moment ago, are the same, then something nice happens. And this makes sense, doesn't it? I mean, if a bunch of A's make up B, and a bunch of B's combined make up C, then yeah, a bunch of A's should also make up C. That's one way to think about it. Let's do some scratch work. To test it out, right? I mean, before you prove something, first of all, you should start writing right away. As soon as you can, start writing things down. Definitions, whatever, examples. Get your brain moving here. So let's do an example. Let's make sure it makes sense to us. So 3 divides 12. Yeah, that works. And 12, this is a real class. You'd be picking these numbers, but alas. 12 divides, I chose 24. But, you know, pick your own examples on your own piece of paper. And does this imply, that's the imply symbol, is it true that 3 divides 24? Is that true? Yeah, check. Yeah, 3 does divide 12, 12 does divide 24. So if this is going to be true, then in this example and all other examples, it must be the case that this number divides that number. And in this one case, it does. Okay. Now, in our Scratch work, it's also useful to always recall definitions. Now, as our propositions and the proofs get more complicated, our Scratch work will take on a variety of forms. But in almost every case, if there's a relevant definition, it should be front of mind, that definition. For example, 3 divides 12 has a definition to it. It says that 12 equals 3 times some integer. In this case, that integer would be 4. Maybe I'll use a different color here. Is that visible? Yeah. So there you go. 12 equals 3 times 4. The 4 is the k in this case. 24 equals 12 times. Is there an integer k that we can put here? Well, there's got to be. If this is true, there has to be one. In this case, 2 is that integer. And 24 equals 3 times, what's the integer? 8. Okay. And remember, we have this handout, this outline for how we generally prove things directly. Okay? How do we prove things directly? Start with what you're given, work towards what you need. I'm pausing because I want you to kind of stare at these numbers and see if anything jumps out at you. Because when we actually are going to prove it, we're going to have a specific A divides B, B divides C, and we want to conclude that A divides C. So we're going to be given, so you think about what you're given, think about what you want to get to. So what you're going to be given is that A divides B. So you're going to be told that, that B is A times some integer. We can't use K for all three, so I'll use S here. B equals A times S. And you're told that C equals B times some integer. Let's call it T. And what do you want to show? You want to show that there exists, this is what we have. What do we want? We want to have C equaling to A times some integer K. So we're given the S and the T, we want to find the K. That means we're given these the first two orange numbers, and we want to find the last orange number. We want to show it exists. But do you notice anything interesting about those orange numbers? What do you notice about them? You might notice that they're kind of related in an interesting way. We have divisibility. Something divides something else. The inverse operation is multiplication, which is explicit in the definition. And what do you know? This number times that number equals that number. See, this is when it's oftentimes helpful to do Scratch work. Sometimes the definitions just sort of the reason why something is true sort of pops out at you. And you're like, oh, well, in this one example, this K times that K equaled that K. I wonder if that's always true. What do you think? Is this just a coincidence or is it always true? Well, let's see here. So, all right, I ended up pausing the video. I moved definition 2.8 over here. So A divides B if B equals A times K for an integer K. Underline that. Okay. And here I started the proof. So, how do these proof outlines go? For a direct proof, typically you start with your assumptions. Assume a, b, and c are integers. Also assume a divides b and b divides c. And at the end, we hope to get down to, therefore, a divides c. So how can we bridge this gap? Well, usually, especially for these early problems, when we've assumed almost nothing, right? We know what the integers are. We have like 3 definitions and a few facts about even and odd numbers. We don't have much. So probably we're going to use the definition of divides. So we have a divides b and b divides c. Let's say what that means. So then, you could say the definition of divides, or you can say the number. So in this case, that number is definition 2.8. But if you want to say by the definition of divisibility, so you don't have to memorize the number, that's fine too. So by definition 2.8, what does a divides b mean? It means b equals a times some s, where s is an integer, for some integer s. And what does b divides c means? It means c equals b times t for some integer, I'm writing bigger, t, integer t. Okay. So good. Now, let's also work from the bottom up. Okay, so what is a divides c? Well, before we get to a divides c, most likely we'll get to the point where we have c equaling a times k for something. We'll fill that in later. K has to be an integer, but we'll get back to that. Okay, so you see, we've kind of moved towards, we've written the last couple lines of the proof and the first few lines of the proof, and we want to see how can we bridge the gap. So do you see a way to do so? Thinking back to the way we proved our first few propositions, does anything jump out to you? Well, if we want to get down to c equals something, here we have c equals b times t. I don't have to write the time symbol, let me just write bt. C equals bt, but we don't want b, we want a. So how do we get an a on this side of the equal sign? The other equation, right? We know what b equals in terms of a. Do you see? So this equals a times s. That's b. b equals a times s. And then we still have that t out there. Got it? So if we're trying to get down to c equals a times k, we're almost there. We have an a and we have an st. Maybe just visually it's the same thing. Maybe I'll group it that way. And now you see, what should our k be? It's the s times the t. That's, by the way, exactly what we noted over here. What's our k going to be in this case? Our k, if this is our s and that's our t, k equals s times t. That's the observation we made before. And guess what? It turns out that's exactly right. That's always true. This little calculation shows it. So now all we have to note is, why is this k an integer? Well, it's an integer because s and t are integers. And way back, remember that fact 2.1? The product of two integers is going to be another integer. Okay. So, and since s and t are integers by fact 2.1, so is s times t. Therefore, C equals A times K for the integer K equaling S times T. And therefore, A divides C. That's the definition of divides. Maybe I'll write that. By definition 2.8. And that concludes the proof. So we can write our proof box. Okay. So there you have it. Wish I could ask if you have any questions, but, well, you could still write in the comments. There you go. Feel free to do so. Great. So, well, this is enough for this video. So we'll pause this video here. We'll stop this video here. And next time, what is next time? Actually, haven't looked ahead. Next time is, let's see, that was proposition 2.10. We'll do the division algorithm. Right. Okay. So next time, this is what it means to divide something. And we have a symbol for what does it mean if you don't divide. And, you know, we could rework the definition to say this is what it means if you don't divide. But there's a little bit more nuance to the situations. Okay, if you don't divide, if A does not divide B, there's some nuance. You can say a little bit more about in what ways does it not divide B. And that leads us to the division algorithm. So that'll be the topic of the next video. All right, see you then.